This is Rich Taylor, Miami University. The topic of this presentation is recrystallization and determination of a melting point. This is typically a good way to take a reasonably purified solid sample and convert it to the highest possible purity. And your index of the purity through a recrystallization is going to be through the melting point, among other analyses. So the scenario we have is at the end of a reaction, you normally have your product, and your product has been purified at least a little bit by some kind of extraction, but it is present in a solution. If the product is a solid, or even if it's a fairly non-volatile liquid, you're going to normally isolate it by evaporating the solvent. If it's a solid product, the solid will normally crystallize upon evaporation. That's not a cinch because even crystalline materials may not crystallize under this crude evaporation technique. Sometimes they will what we call oil out. They'll drop out of solution so fast that the crystals don't really have time to form well. But oftentimes, if the product really is a crystalline solid, you can eventually get it to crystallize. This will usually involve taking a concentrated solution and beginning to evaporate it slowly, scratching the sides, heating and cooling. The best way, if you actually have an authentic sample of the crystal, is to seed it with a little bit of the crystal to get the process started. Once you obtain that crude crystalline solid, it may be off color. Its melting point may be a little bit low. That's usually a sign that there's some kind of impurity so that you need to further purify it, and recrystallization is a good option. In the essence of recrystallization, what you're going to do is add an appropriate solvent and heat that up so that the solid dissolves. You're going to boil off some of the solvent until it's just about saturated, it's just beginning to drop out of solution and is a little bit cloudy, and then you're going to cool that solution and let the crystals form. You're going to isolate those crystals by vacuum filtration then and check the melting point and repeat that process as many times as necessary to get really pure stuff as denoted by a constant melting point. The crucial thing in doing a good recrystallization is choosing the solvent. That's actually the hardest part of the job. Ideally, what you want is a solvent in which your product is very soluble hot, very insoluble cold, and in order to achieve that, you're going to need to do some experiments. It's great when a procedure gives you the solvent, but if not, you're just going to have to use some thoughtful trial and error. The best solvents are ones that have a reasonable boiling point, melting point differential. Essentially, you want to be able to heat it up hot enough so that it gets good solubility, and you want to make it as insoluble as possible. That's going to involve cooling it as much, so the wider the range you have between boiling and melting point, the better off you are. Examples of this. Benzene is a poor choice for a recrystallization. It's toxic, and it also has a melting point that is above 0 degrees. So if you place a benzene solution in an ice bath, you'll get lots of crystals, but those crystals are actually frozen benzene, not your product. Likewise, ether is often used, but is usually a pretty poor choice. Its boiling point's too low. And so as a result, you can't really get a lot of solubility by heating. Also, ether's somewhat flammable as it's boiling, and so you want to try and avoid that. Hexane actually works pretty well. As organic compounds go, it's rather polar, so it's good for dissolving lots of things, and its boiling point's around 77 degrees, so you can boil it away, but you are actually at a fairly high temperature. If you want a non-polar version that has about the same boiling point, hexanes or petroleum ether, which isn't an ether, it's actually a hydrocarbon, they're both very non-polar and have a good boiling point as well. So as a result, you can see that there's some rationale to using a mixed solvent. If you use ethyl acetate and PET ether or hexanes together, you have a very nice system. They both boil at the same point, and so you can change polarity by adjusting those proportions. So a good scheme then would be dissolve the material in hot ethyl acetate, then slowly add petroleum ether until you reach that saturation point. Then if you take away the heat, you're going to cool and collect the crystals at that point. Since the boiling points of ethyl acetate and petroleum ether are similar, you don't change solution composition while you boil things away, at least not very much. Pitfalls. What makes recrystallization a real difficult proposition? One is that many students are so yield happy that they evaporate too much solvent, trying to get too much stuff. So essentially what the student winds up doing is dissolving it and then completely evaporating the solvent. That doesn't take away any impurities. And as a matter of fact, the excess heating that you get as you drive off the last of that solvent winds up charring the sample. So you're actually worse off than you were at the beginning. Another problem is poor recovery. That generally comes from choosing a solvent that was a little too good in terms of dissolving the product. So you can sometimes recover some and then perhaps boil away a little more and do what we call getting a second crop out of these things. But typically what you want to do is pick the ideal solvent and work as hard as it takes to arrive at that one. If your compound is colored, sometimes it's useful to use activated carbon or activated charcoal, it's sometimes called, in order to remove some of the color. Color is very deceiving. A very little bit of a highly colored impurity can really make your product look bad, and so it's sometimes difficult to get that last bit of color out of there. Activated carbon is a material with a high surface area and a lot of polarity, so colored molecules really tend to stick to it. You lose some of your material when you do this, but if you really want stuff that has no color at all, activated carbon may do the trick. So what you do is, while the solution is still hot, you drop in a little bit of activated carbon, swirl it around for a while, and then filter very quickly while it's still hot, remove all of the activated carbon, and the material that crystallizes out has a lot less color. Sometimes activated carbon is so finely divided that it will often seep through the actual filter paper, and so using sea light as a filter aid to help your filtration become more efficient is sometimes useful. Once you have this pure crystallized solvent, you're going to want to take a melting point. Melting range should be at the literature value, and it should be a quite narrow range. The melting point can be determined in a variety of different apparatuses designed for the purpose. They all include some way of introducing the sample, some way of heating, a way of looking at it so you can see where at what point the solid melts, and a temperature probe to tell you what that temperature is. Often these involve placing the material in a capillary tube and then putting them in an oil bath. When you use one of those kind of melting point apparatus, you're going to want to make sure that your solid gets all the way to the bottom and has good contact with the glass, often by tapping at the bottom and forcing the thing down there. Other ones have you placing it on sort of a microscope slide or microscope stage and placing it on a heating stage, and then you heat up the solid block and observe the temperature while you look at the solid in a magnifying glass to see where it melts. On the considerations that come from doing a melting point determination is usually you're going to report a melting range and not a single point. So you want to go from the point where the material begins to soften the crystals until it's completely gone, and that range is your melting range. It needs to be solvent free. You want to be melting the crystals, not dissolving them in a little bit of residual solvent. Likewise, you can't go too fast through the melting point. It takes time for things to melt, even if they're all willing to melt at that point. If it takes you, if your temperature ramp is so high, you're going to have a wider range than is really realistic for your material, because in just the time it takes to get that sample melted, your material is going to wind up being at a higher temperature. Your best practice then is to know the melting point when you get started. That's either done by looking in the literature or doing a quick run through to see about where that point is. Then you can go back down to lower temperature, reintroduce your sample, and heat up rapidly until you get close to the melting point, and then move very slowly through that little range. That'll give you the most accurate reading of your actual melting point. With this knowledge in hand and with a little bit of practice, recrystallization and taking a melting point is going to become a fairly routine process.